Hey guys, this is Aaron Carmen from AXE Electronic, back with the next video in our series of videos covering basic circuit analysis. So today, as you can see, we're going to be talking about combinations of capacitors and inductors. Now, if you remember, back closer to the beginning of this series of videos, we talked about how we can treat resistances in parallel and in series. Okay, so if we have two resistors in parallel, we can combine them into an equivalent resistance. We can also do the same thing for two resistances in series. So it turns out we can actually do the same for capacitors and inductors. Now it's going to be a little bit different, so it's important to watch this video and make sure you get a good understanding of this. Okay, so like I said, they are going to be a little bit different, but for today we're just going to talk about an intuitive explanation and not really get into the heavy math that's involved. If you want to know the math, I'm sure that there's plenty of good articles out there, but for the purposes of just understanding why we're doing the things that we're doing, I'm just going to talk about a very broad level sense of things. Okay, so we're not going to dig into the math. Okay, so the first thing we're going to talk about is capacitors. So how are we going to treat capacitors if they're in parallel or if they're in series? Okay, so the first thing to remember is that capacitance, C, is equal to Q, which is charge, divided by V, which is volts. So the amount of charge a capacitor will store for a given voltage. So if, for example, you have a 1 farad capacitor, then you can store 1 coulomb of charge if you put 1 volt across that capacitor. Okay. Now, if you have that same 1 farad capacitor and you put 10 volts across it, then you're going to be storing 10 coulombs. Okay. So you can see the relationship between charge and voltage in these capacitors. So let's say that we have two capacitors in series. Okay. So we have two capacitors in series like this. Let's say that we have a supply voltage of 2 volts, and then this is C1 and C2. They're each 1 farad. Okay. Now, what you'll notice is that since these two capacitors are equal and they have a shared voltage drop, since everything is equal, they're going to just have 1 volt each across them. Okay, so they're just going to have 1 volt each across them, and excuse me, each of them is going to be storing. Remember, if we look at, let's just look at this capacitor at first. We have 1 farad is equal to the amount of charge Q divided by the voltage, which is going to be 1 volt. So we can solve for Q and find that Q is going to be equal to 1 coulomb. Okay, so each of these capacitors is going to have 1 coulomb. So 1 coulomb of positive charge on the top plate and negative 1 coulomb of charge on the bottom plate. All right, and then it's going to be the same thing for each of these. All right, because they're two equal capacitors. Okay, so now let's look at this a little bit more so we can see how much charge is the source having to supply. Okay, so you might be tempted to say, well, it's supplying 2 coulombs, but that's actually incorrect, because what happens is that whenever we supply 1 coulomb to this first capacitor, so we get some charge, we get 1 coulomb of charge on that top plate. What that's going to do is that's going to repel 1 coulomb of charge from the bottom plate and turn it negative. Okay, but that 1 coulomb of charge from the bottom plate has to go somewhere, so the only place it can go is to this next plate, which again repels that same charge. So you can see that if we put 1 coulomb on the top plate, okay, it's going to repel 1 coulomb and send that to the bottom capacitor. Okay, so the total amount of charge that the source is supplying, is just 1 coulomb. Okay, so I'm going to go ahead and just write over here, Q total is equal to 1 coulomb, the total amount of charge that is being supplied into those capacitors. Okay, so now let's look at the voltage that we're applying. Okay, let's look at the voltage that we're applying. So the voltage across both of those capacitors is just going to be 2 volts, right? It's just the supply voltage. So we're going to say the voltage is equal to 2 volts. Okay, so we know charge, we know voltage. That's enough for us to calculate the equivalent capacitance. Okay, so I'll draw it over here. We'll still have the same 2 volt supply. Now we're just going to have this CEQ here. Okay, and then the CEQ is going to have 2 volts across it, and it's storing 1 coulomb of charge. Okay, so now we can calculate. Let's do CEQ is equal to, remember it's charge, so 1 coulomb divided by the voltage. Okay, so what we'll find is that this equivalent capacitance is 0.5 farads. Now remember, both of these that we started with were 1 farad. So what this tells us is that combining capacitors in series actually reduces the capacitance. Okay? And the reason behind that is because the amount of charge is shared between the two capacitors, right? So they have the same amount of charge, but smaller voltages. Okay, so because of this, adding those capacitors in series is going to actually reduce the effect of capacitance. Okay, so we can get a formula, and you'll notice that this formula is pretty similar to the one for parallel resistors. C equivalent is going to be C1 times C2 over C1 plus C2. Okay? So this is the formula for capacitors in series. If you want to change it into an equivalent capacitance, capacitors in series, you're going to use this formula here. Okay? So notice this is just like resistors in parallel. So the same formula for resistors in parallel is going to be used for capacitors in series. Okay? So now let's look at another example. Okay? So let's see what happens if we have parallel capacitors. So let's say that we now have a 1 volt supply. And then we have this 1 farad capacitor, and then another 1 farad capacitor. I'm just using 1 farad to keep the numbers simple and kind of make it easy to work with and see without having to write down a whole bunch of math equations. So, you can use any numbers you want, it's still going to work out, but I'm just using 1 farad to keep things easy. So you can see each of these is going to have 1 volt across it. Okay. Now, if we know the capacitance and the voltage, we can tell the amount of charge that's stored. So this one is going to have the same 1 coulomb of charge stored. This one's going to have 1 coulomb of charge stored. So now let's ask ourselves, once again, how much charge is that source having to supply? Well, this time we're supplying 1 coulomb to the left capacitor, 1 coulomb to the right capacitor. So the total amount of charge is going to be 2 coulombs. Okay. So now this gives us enough information to get an equivalent capacitance. So I'll redraw the circuit. We have 1 volt, and we want our equivalent capacitance, Ceq. Well, we know that the voltage across it is going to be 1 volt, except now we've supplied 2 coulombs. Okay, so we know the charge, we know the voltage. That gives us enough information to calculate the capacitance. So let's say Ceq is equal to charge divided by voltage. That's going to be 2 coulombs divided by 1 volt. It's 2 farads. Okay, so now you can see adding capacitors in parallel increases the capacitance. Okay, so adding capacitors in parallel increases the capacitance. And we're going to be using this formula. The equivalent capacitance for capacitors in parallel is going to be C1 plus C2. So notice this is the same for series resistors. So capacitors, if they're in series, you're going to use the formula for parallel resistors. Okay, and if they're in parallel, use the formula for series resistors. So they're a little bit backwards from resistors. So that's a note that I want to make. I want to say capacitors, so I'm just going to use C's, are opposite of R. Okay, so that means that if we have 2 capacitors in parallel, what we're going to do is we're going to use the formula for resistors in series. Okay, so you don't have to remember this, you can just remember the formulas, but I think that's a good way to sort of jam it into your brain that capacitors, they use the opposite formulas, that capacitors are opposite of resistors. Okay, so now this is how we handle those combinations of capacitors. Okay, so let's look at an example. So let's say we have a source. We don't even need to know the value of this source for this one. Okay. We have these 2 capacitors in series like this, and then 1 in parallel. So this is going to be asking, let me sort of move this down a little bit so I can write the problem. I'm going to ask, what is Ceq? So what is the equivalent capacitance that source is seeing? And we need to know the values of this, so this is going to be 3 farads, 6 farads, and 2 farads. Okay. Well, the first thing we can do is we can say, well, these 2 capacitors are in series, so we can simplify that. So let's go ahead and do that. I'll rewrite this circuit. So now we're just going to have a single capacitor there and a single capacitor there. We know this one is 2 farads. Okay, so what is this? I'll call it Ceq1. Well, Ceq1 remember we're going to use the parallel resistor formula for series capacitors because they're backwards. Okay, so if we use the parallel resistor formula, that's C1 times C2 over C1 plus C2. So then we can say this is equal to 3 farads times 6 farads over 3 farads plus 6 farads. So this is going to be 18 over 9 or 2 farads. Okay, so this CEQ1, this equivalent capacitance, is actually 2 farads. Okay. So now you'll see we have 2 capacitors in parallel. We can simplify this again. So let's do it. We'll have that source. We're changing this into just a single capacitor. All right. Now I'm just going to call this CEQ. Now what's the formula for that? Well, if we have 2 capacitors in parallel, we're going to use the formula for series resistors for parallel capacitors. Okay, so CEQ is just going to be the sum of the 2 capacitances, C1 plus C2. So in this case, it's going to be 2 farads plus 2 farads. So the equivalent capacitance is going to be 4 farads. 4 farads here. Okay, so you'll notice this is kind of similar to how we did the DC circuits before with resistors. So we would say, okay, here's some series resistors, or here's some parallel resistors. Simplify those, and then that would let us simplify something else. Okay, so this is the same thing, the same instance in this case. So the only difference is the formulas are a little bit different. Okay, so this is how you're going to work with these capacitors. Now we need to talk about how we're going to work with inductors. Okay, so let's go ahead and scroll down and start a new section called inductors. So how are we going to handle series and parallel inductors? Okay. So first thing, let's go ahead and look at some inductors in series. So let's say we have this source, which I'll call Vs, and then we have 2 inductors, L1 and L2. Okay, so this is L1, this is L2. Okay. So now, one thing we need to remember is that inductors resist current. Oh, sorry. So we need to remember inductors, so L's, resist a change in current. So if these inductors don't have any current flowing through them initially, they're going to resist that change in current. And then the next thing we need to know is that VL is equal to L di dt. Okay. So now with this simple circuit we have, let's just do KVL on it. So KVL, remember, is the loop rule. It says the sum of the voltage rises and voltage drops has to be equal to 0, or the sum of the rises has to equal the sum of the drops. Okay? So let's do KVL on this circuit. So if we start here in the bottom left, we'll see that we first have a voltage rise, Vs. Okay? So Vs is going to have to be equal to VL1 plus VL2. All right? So now let's plug this formula in for both VLs. Okay? So Vs is equal to L1 di dt plus L2 di dt. Okay? Now we can factor out that di dt, and we can say Vs is equal to L1 plus L2 di dt. So looking at that, we can say, well, I mean, this sort of just looks like an equivalent inductance. And if we rewrite this to say Vs is equal to L equivalent di dt, you can see that looks pretty much just like this formula we had all the way up above. And that looks pretty much exactly like this formula here. Okay? So what we can say is that if we have 2 inductors in series, okay, their inductances actually add. Okay, so inductors, you're going to use the same formula as a resistor in series. So I'll just write this over here. Leq is equal to L1 plus L2, okay, for series inductors. I'll use for series Ls. Okay. So series inductors, their inductances are going to add together, okay? So they're like resistors in this sense. Okay, so like I said, inductors in series add. And this kind of makes sense because if we think about it, there's going to be a current flowing through each of these. Inductor 1 is going to resist that change in current, and then inductor 2 is also going to resist that change in current. So they're both resisting a change in current, and you can think of they're resisting a change in current. They're like resistors, so resistors in series are going to add the same way inductors add. Okay, so now let's look at them in parallel. So let's say we have a circuit. It's going to be Vs, and we have two inductors in series. So this will be L1, and this will be L2. Okay, so now each of these inductors is going to have a current running through it, right? And that current is going to be proportional to the equations that we used above. Okay, so the sum of these currents is what the source is going to see. So let's say this inductor is going to have a current that rises like this, and this other inductor is going to have the same way, that a current that sort of rises like that. Now, the source is having to supply both of those inductors, so it's going to look like the current rises a whole lot quicker, right? Because you have two inductors in parallel. They're each requiring their own current, right? So it's going to look like the source is going to see a current rising quicker. Okay, so because of this, the source is going to see a current that rises 2 times as fast, which sort of translates to having half as much inductance, right? Because last time we said if you have a higher inductance, that sort of corresponds to a slower circuit, right? So if you have a circuit that's rising faster, that's behaving faster, then your inductances is getting smaller. Okay, so again, just like resistors, inductors in series get smaller. Not in series. Inductors in parallel get smaller. Inductors in parallel get smaller. So we can use the same formula for resistors, and we'll say LEQ is equal to L1 times L2 over L1 plus L2. Okay, so if you have inductors in parallel, that's going to be reducing your total inductance. Okay, so the formulas for this is pretty much going to work out exactly like it does for resistors. Okay, so I'm not going to go through any examples because we've already done some examples like this, and we just did an example with capacitance. But I do want to summarize, because this is going to be sort of the most important thing to remember. So I'm going to summarize. So if we do a little summary of these formulas, I'm going to say, let's have one for capacitors, which I'll call this caps, and then inductors. Okay, so capacitors, if we have them in series, okay, series capacitors, remember, it's like the formula for parallel resistors. So it'll be C1 times C2 over C1 plus C2. For inductors, if we have inductors in series, it's going to work the same way as resistors. Okay, so inductors in series is just L1 plus L2. So now, let's see if we have parallel. Well, parallel capacitors, remember, they're going to use the same formula as series resistors. So these capacitances are just going to add. Right? Now then inductors, those are going to use the same formula as parallel resistors. So it'll be L1 times L2 over L1 plus L2. Okay? So the big takeaway from this is going to be capacitors use opposite formulas. So capacitors use opposite formulas. So if all you remember are the formulas for resistors, then you need to remember that capacitors are going to use the opposite formulas. So if you have capacitors in parallel, you're going to use the resistors in series formula. If you have capacitors in series, you're going to use the opposite, which is resistors in parallel. Okay? And then inductors use the same formulas. So if you have two inductors in series, then you're going to use the equation for two resistors in series. And the same thing, two inductors in parallel, you're going to be using the equation for two resistors in parallel. Okay, so this is everything that I had for you. I hope that this was informative and that you learned a little bit about how you can combine capacitances and inductances. So next time we're going to be doing some examples over these circuits. It's going to be like we did previously with our resistive circuit analysis examples. So I'll have 5 different examples that all have capacitors and inductors in them, and we're just going to work those out. I'm not going to have any notes in front of me, so you're going to see how I work them out, and you can work them out your own way, and I'll make sure you have all the answers so you can verify that things are working. And in addition, in our previous video, we also looked at how we can simulate these circuits. So if you have some questions, or you want to try simulating, or if you want to try doing your own circuits, you can always check your answers by using the circuit simulation software. So if you have any questions, please feel free to leave them in the comments below. If you like this video, please give me a thumbs up and subscribe for more content. Otherwise, I'm Aaron Carmen, and thank you for watching.